Okay, let's talk about the second day of the tutorials, just before the trans magnificent presentation tomorrow. Record, okay? Well, I mean the present and the record, okay? So we will talk about some more practicals, some optical properties of the single wall carbon nanotubes we are always all the day dealing with. So for that, we need to know just two basic concepts, so absorption and fluorescence. That is all most of the things we need to know. There's also other things to, for example, two photons, absorptions, and some triplet emissions, so it's a phosphorescence. But most of our practical point is that we will dealing with the absorption and the fluorescence. So thinking about what is the absorption, so absorption means that the photon is absorbed by the materials. So, but what really happens in the absorptions, to look into more deep into what happens, is that actually they are more electron-like, electron-related phenomenon. So assume that there is the electron at the ground levels. The ground level means that they are mostly or most stabilized state. So electrons, when they are absorbing the photons, that is absorptions, the photon will have the energy of the E is equal to, we talk about later, the photon's energy E is equal to the Planck constant 664 times 10 minus 44 joule per sec cross frequency. So actually photons energy is the functions depending on the linearly proportional to the frequency, and the Planck constant is just a constant. So assuming that, for example, this photon has the 600 nanometer wavelengths, we can calculate this frequency by the wavelengths speed of light, so that we can calculate the frequency is 600 nanometers and the speed of light is 3.10 to the minus 10 to the 8 meter per second, so that we can calculate the frequency. So when the photons of that frequency comes, only absorption happens is when the ground state electrons and there is excited state. Excited state means that more higher energy. There is the electronic state or energy state corresponding to that energy. So for example, if the energy level is like this is the ground level, and the excited level 1, excited level 2, excited level 3. Even though the photons which have the energy corresponding to this, they are not absorbed. So only the absorption happens, the photon's energy is corresponding and matching to this energy gap, or this energy gap, or this energy gap. So that is the quantized, the kind of quantum mechanics phenomenon of the absorptions. So in that way, what happens in the carbon nanotube is, so we learned about the electronic state of the carbon nanotubes. They have the like this kind of the main energies, like the E1 ground and E1 excited, and there's E2 ground, E2 excited. So mostly the electrons are filled out to these levels. The electrons are filled, the electrons are not filled. The absorption happens that when energy comes to this energy gap. So then absorption spectrums in E11 transition peak happens in here, and E22 transition peak happens here. Because the E11 transition peak is corresponding to this energy gap, they are showing the absorption spectrums. but slightly more lower energy in the lower wavelengths. That means that more higher energy. So this higher energy, there is no corresponding energy gap, energy state, so they cannot be observed, or they do less observed. So that is what we are showing, what we are every day seeing in the absorption spectrum of the carbon atoms. So then after the absorptions, the electrons are excited to the more higher energy levels. Then there is the one excessive electrons in the excited state, and there is one shortage. So one electrons are lacks. So in these ground levels, these ground level electrons are feeling like there was many electrons are there, millions and not millions, and more than thousands in carbon atoms. And excited levels, there's one electron that happens. So in here, these empty energy states are filled like the positive charge. Because once there was electrons, but now the electrons was gone. So it looks like we can consider that as one positive particle. So it is what we are called hole. And these electrons, the only electrons in the excited side, we can call that as the just electron. So because of the electromagnetic force, they are moving together. So we are usually calling that electron hole pair, or in other words, exciton. So that means that we are calling the two particles as the one kind of the particle, like the excitons. So that is usual. We are showing, you are seeing in the papers. So I already explained. And the other things is that usually these levels is called balance level. Balance. Not the B balance. It is we need the outer shell balance levels. And these levels, which is not filled with electrons, are usually called the conduction level. So that is why they are naming it by the V1, balance level 1, balance level 2, and the conduction level 1 and conduction level 2. And you may be ask that why then it does not happen the transition between the V2 to the C1. That could have happened because there are these electrons filled in here, and at the C1 there's electrons are not filled, so they are more free to accept the electrons. But that is not possible. The transition is forbidden by the quantum mechanics. So only the 1 to the 1 and 2 to the 2 transition is allowed. So this transition is the 1 to the 2 or 2 to the 1 is not allowed. So just accept. So then what we are usually seeing in the absorption spectrum is that absorption spectrum is not as clean as these lead ones. Usually they are more dirty like these black ones, because why? The carbon atoms, what we are using is not single chirality. This is the mixture of the different chiralities. So actually the absorption spectrum is more like the mixture of the multiple chiralities. For example, these light figures, there is X region is the wavelengths, and Y region is the absorbance. Then actually what we are showing that is this kind of broad spectrums, but actually in the broad spectrums, hidden figure is that many kind of the single carbon atoms are there, and when deconvoluted properly, we can find out how much carbon atoms in each chirality is having inside of the solutions. So in the industries and the applications, it is kind of now issues and challenging point to how to use the single chiral carbon atoms, not using the multiple chiralities. For example, that is possible. So if you are doing the chiral sorting, the Yunsa is doing some things before. So many chiralities, when they are showing the different chiralities, you can see that they have different E2 to transitions. And E2 to transitions are usually in the range of the visible light. So in other words, single colority in human eye looks different color. So if you are properly sorting out in some way single colorities, for example, 8.5 and 9.6 or 6.5 here, it is most dominantly used. They are showing color. Like 6.5 is usually purple colors in my eye, and 8.5 is yellow color. So it is not just beautiful, it is quite useful for many applications. For example, in the biomedically, if we can detect each carbon nanotubes chiralities, for example, in the cells, then carbon nanotubes was incubated and carbon nanotubes started to infiltrate inside of the cells. So in the just spectrums, usual spectrum, it looks like that because there is many chiralities are exist. But for example, hyperspectral imaging, some techniques, they can differentiate each wavelength differently. Then actually there is multiple different chirality is mixed inside the one image. And we can color them separately. For example, 1,000 nanometers as the purples and 1,200 as the yellow and 1,300 is lead. And we can pseudo color. We can pseudo color each carbon nanotubes differently. Then, for example, so 1,000 nanometers carbon nanotubes go to the normal cells, and 1,300 nanometers can go to the cancer cells. So we can using some kind of multiplex, multispectral imagings by using different or confined chiralities. And which is more actually having attention is that in the electronics, in semiconductor field, carbon nanotube is very well confined, just 1 nanometers or below 1 nanometers circuit. So they do not need any kind of photolithography. They are just one very thin wires, which has very good conductivities, controlled conductivities. The problems now, the single word carbon nanotubes in the electronics and semiconductors is, it is not single chiralities. It is not single chirality. What it means is, for example, silicon. Silicon is the main semiconductor we are using in the semiconductor industries. Silicon kind of silicon bulk has the electronic band gap around 1.0 electron volts. So they are starting to absorb usually about 1,000 nanometers. So below 1,000 nanometers absorbing, but after the 1,000 nanometers, they are not absorbing. So they have, all the silicons have the same band gaps. So band gap, same. So core and the electrons, when they are moving, they are moving like very nicely with the same band gap structures. But assuming that carbon nanotubes do not have the same band gap because of the chirality. So one single carbon nanotubes may have the band gap of about 1.1 electron volt, and this another carbon nanotubes will have the 1.2 electron volts because of the different chiralities. So then what happens is forces are moving and electron trapped. So without the same chirality, if we can mass productions single chiral carbon nanotubes, then maybe this very interesting things happens in the semiconductor industry. So tremendous of the monies you can gain, but it is not yet possible. So chiral sorting itself is okay, but mass production is not easy. Okay, so that is about the absorptions. So we are talking about the emissions. So like fluorescence. So actually emission is the more broad term. It includes the fluorescence and phosphorescence and persistence luminescence and whatever. So actually fluorescence and phosphorescence are quite different process, slightly different process. But we are usually talking about fluorescence. So fluorescence is defined as the when of materials or anything when after they absorbing the light and after they excited, the excited energy is emitted by the light. That's the fluorescence usually. So for that, you can say that it needs absorption at first. By the absorption, what happens is that these ground state electrons are excited by the corresponding energy photons, and these electrons are moving to the excited state at first. So that is the absorption. And at the absorptions, what happens is the electrons are moving fastly to the ground state of the excited state. So most low level energy state of the excited state, the electrons are moving. After that, usually the fate of these electrons is two ways. First thing is that they are moving to the original state. In what way? Non-fluorescence way. So that's what we are calling non-radiative decay. So electrons are here moving excited pores, and because they have the electrical attractive field, so they try to move into the more stable state. So there's two ways. One is a non-radiative decay, which means that not related to the radiative, so light. So they can move into the ground state without emitting light. So then, but energy should be conserved. You see, energy should be conserved. Then how does this decay happens? What happens? It making heat. So non-radiative decay is usually about by using the vibrational state, this energy is emitted in the heat form. So temperature is increasing. And the fluorescence is that when the electrons are without the intersystem crossing, not important now. So symbol like singular state. So radiative decay, decay is that these energies made by the absorptions are emitted in the form of the photons. Then what we are calling that is fluorescence. And when intersystem relaxation happens, intersystem crossing happens, so it does not very important, but assuming that there is electrons, where is that? The electrons, they have the spin actually, the spin up and down. So assuming very simple considerations, there is one up spin electrons, one down spin electrons. And when the photon is absorbed, these electrons are moving to the excited state by conserving the spin. So they will be the down spins. So when they are fluorescence, just down spin moving to the down spin. But what intersystem crossing happens when these electrons are converted to the different spin, up spins. Then total spin of this one and this one is that it is, for example, +2 plus half. It was minus half. So total spin was 0. But when they are converted, the spin is reversed. That up spin and up spin, so total spin is +1. So we are saying that this state is a singular state. This is the triplet state. And triplet state to the single state conversion is forbidden, so it takes some time to make that happens. So usually after the intersystem crossings, these electrons, when they want to go to the basic state, it takes more time. So this fluorescence is the more faster process, and this phosphorescence process is more slower process. So usually this kind of phosphorescence happens when we are doing 인광. Some kind of more long-lasting fluorescence or long-lasting emissions that can be used for this kind of process, but not very related to the carbon nanotube case. And getting to the more difficult stories, to explain what is the then, you can understand what is this borderline S1 and what this borderline S0. But what is this stem-like state? That is the very interesting. So we are usually talking about that this is the most electron transition. Electron transition is not purely electronic. So this energy state is the electronic state. But actually, I'll show you that, for example, if you are seeing the fluorescence spectrums, it looks like this. Not just line spectrum. It looks like some kind of broad spectrum. It has some kind of the width, for example, 50 nanometers or 40 nanometers. That means that there is not just one photon of this energy. There is photon of this energy, this energy, this energy, this energy. But what I'm drawing at first is that this is the valence level, this is the conduction levels. It looks like these very sharp, discrete energy levels. So if this is the only energy levels they have, it should they should have like this kind of very sharp fluorescence. But actually, in reality, this broad spectrum happens. That's why one of the reasons is that the state of the electrons are not just the electrons, they have the mixture of the vibrational state and rotational state. So for example, this electronic state is the mostly high energy state. They are dominating most of the energies. But inside of the electronic state, there is vibrational energy that comes from the temperatures. With the low temperatures, vibration of the molecules are more slow. Higher temperatures, the vibration of the molecules are more fast. That means the more higher energies. So actually there is the vibrational quantum energy levels at each electronics. So when very low state, the vibration energy is mostly at the, electrons are mostly at the ground state. But at the usual room temperature is as we talked, it is about 300 K. At the 300 K, electrons are mostly in the here, but also here, and also here, and also here. So what usually happens is the vibration state, there is also electrons. Like here. So it is possible, for example, the transitions like this, and transitions like this, and transitions like this. So slightly there is different energy. It happens by each fluorescence and absorptions. That is making this kind of broadening of the fluorescence and absorptions. And also more smaller energy levels, vibration energy levels is also there, and rotations are there. So for example, the carbon nanotubes are here, carbon nanotubes do not have rotation energy usually like this. Making these different examples. For example, this ethane. CH3. So these molecules can have the vibrational state. That is making this kind of low energy level state. But actually, they can also, at the temperatures, they can rotate. Like they can rotate in this way, and they can rotate also at the this axis. And they can also rotate like this way. So that rotation energy is also quantized. They are making also, even though smaller than vibrations, they can make more smaller each energy state at each vibrational energies. That is the contribution of the rotational energy, but it's usually more smaller than the vibrational. So we usually need that to consider. Usually in the carbon nanotubes and the room temperature, what we are consider is the electronic state and the vibrational state. So something we are showing that when we are taking our fluorescence or at fluorescence of the carbon nanotubes in the room temperatures, around the decay, it looks like fluorescence spectrums like, for example, we see 15 nanometers. But if we are taking the fluorescence at the more lower temperatures, for example, 70K, then what happens is that electrons, at first maybe at the 300K, the vibration levels are filled like on these levels. But at the 70K, the electrons are losing their temperatures and maybe filled in only this way. And what happens is that they are more like a single level. So in the fluorescence, what happens at a lower energy is that fluorescence is getting more sharper. And if you increase the temperatures, reverse happens because the vibration states are filled of the more higher levels. So the fluorescence spectrum is getting more fat, more broad. So that will be you can consider when you are doing the temperature dependent experiment. So it is kind of not very interesting, but so that how fast it happens, the fluorescence or other things happens, maybe good to know in some days. The fluorescence in the carbon nanotubes after they are absorbed, and they are these excited electrons are moving very fastly to the ground level of the excited state. That happens very fastly in the like 10 to the minus 15 second. So that is called the vibration relaxation, 10 to the minus 12, okay, picosecond. And after that, these electrons are starting to waiting to go to the ground state. That is usually happens in the non-radiative way and radiative way. Carbon nanotube case, it happens in nanosecond. So 10 to the minus 9 second. So in the humans, it is looks like very transient, but actually they can be monitored. For example, the 2023 papers, they are showing the fluorescence decay of the SWCNT in the 165 carbon nanotubes for the dopamine sensors. You can say that x-axis is the time, nanosecond, and y-axis is the fluorescence. So after the carbon nanotubes was excited by this dotted gray line, the fluorescence start to be monitored. So they are not very abrupt. So they are decaying by the time dependency inside of like some nanosecond or sub-nanosecond scales. So actually they are not transient. They have some kind of decay constant to the fluorescence happens. So for carbon nanotube case, as I told you, it is usually between the 100 picosecond to the several nanosecond. That's usually fluorescence decay times of the carbon nanotubes.
So what I need to emphasize is that the fluorescence does not happen all at once. The fluorescence always, it is also kind of the kinetic phenomenon. So assuming that 100 electrons are in the excited state, after the 1 second, 1 nanosecond, 10 electrons are decaying. After 1 nanosecond, another 10 nanosecond, 10 electrons are decaying. So this kind of more probabilistic, stochastic process in the more shorter time scales. So, and last, I will just briefly talk about the more and more practical ones, the COFO-MOR, the corona-phase molecular recognitions we are using for as the sensors usually. So COFO-MOR molecular recognitions, these corona-phase molecular recognitions, the molecular recognition means that whatever these carbon atoms can bind, so recognize some molecules. By what? The corona-phase. The corona-phase can be made by the carbon nanotubes and with some polymers. For example, there is nanotubes and the polymers, which is the blue region is more hydrophobic, which means that it does not like water. Actually, not really. But hydrophilic is described by the red colors. Then the surface of the nanotube is more hydrophobic because it is just carbon sp2, so it does not have any dipoles. So hydrophobic polymers are observed on the surface of the carbon nanotubes, and this hydrophilic part will more friendly with the water. So outside is not water, so they are trying to make more large contact areas with the water. But they are making some kind of the 3D structures on the surface of the carbon nanotubes. That is what we call what? Corona-phase. So corona-phase is the mixtures, the combination by the carbon nanotubes and the polymers. So that is what we are saying the corona, because corona comes from there is a sun, at the sun outside at the line of the sun, the flare happens. The flare is what we are calling the corona first. And these polymers are making the structures onto the surface of the carbon nanotubes. So that looks like the corona of the sun. So they are calling it as corona. Not very intuitive. So this corona phase can be different by the carbon nanotube chiralities and mostly the nature of the polymers. When they are using the different hydrophilic polymers and different hydrophobic polymers, they are making different corona structures. And by different corona structures, they are making some kind of binding pocket for specific analyte. So that is what they are calling the corona phase molecular recognitions. So then, so for that, at first, the carbon nanotube need to be dispersed by the surfactant at first. So there was some iconic papers in 2001 as well as 2002, the Richard Smalley, we talked about yesterday. The Richard Smalley lab are publishing how to make the individual single word carbon nanotubes by the tip sonication with the surfactant. So that was about 10 years after the first carbon nanotube papers, the 2002. So that was the start. We can use the single word carbon nanotube singly, not just bunch or some aggregated ones. And they can start to measure each band gap fluorescence of the individual carbon nanotubes. So there is some kind of familiar names, Mike Cornell's, Sergei Batsleo, and Michael Stern also there. And there is also Han Hutun, and also Bruce is there, and Richard Smalley was there. They were collaborated before. And so after also about 10 years after the first individual carbon nanotube papers, the corona phase molecular recognition was first used in this paper, as I remember correctly, so 2013 in Nature Nanotechnology. In the microstrano laboratories when after they moved to the MIT. Also, there is a familiar name like the Mark Landry, one of the first author. As I remember, the Zhang and Landry and Baron, the three people are co-first authors. And Jong Kim, now in Hanyang University, was there. Artemis and Sebastian was there. Okay. And Hyung-suk is there. Anjino is there. Several familiar names. So after these papers, they start to disperse carbonates with the multiple different surfactant, and at the different surfactant, they try to take the incubation with 40 different analyte. But they are showing that different synthesis polymers, when they are lapping onto the carbonatoes, they are showing different responsibility to the analyte, for example, dopamines or riboflavins or vitamins. So that was the first papers, as I remembered. So now we are after 10 years after that. So but some kind of unresolved question was that why? So when the corona page happens, it is very very intuitive. They can bind into the analyte. So they have some kind of stabilized interactions, but why the carbonate fluorescence changes? That is always we are getting, that is the questions we are always getting from the conference. Why the fluorescence increase? Why the fluorescence quenching? So that is unsolved problem for each specific areas, but to prepare any conference, you need to know that it can be happening, but we don't know why. So for example, the carbonatoes in here, and when they are absorbing the electrons, what we are calling is that exciton happens. Electrons, excited electrons, and holes. This exciton pair is engaged after absorbing the light. So the process is that these electrons and holes are recombined, then in radiated way, then the fluorescence happens. Then the point is that if we can, interrogate their interactions, we can change the fluorescence because we can change the kinetics, this fluorescence decay rate. If we can change the rate, then we can change the fluorescence intensity. So then it is more natural. The carbonate with the electron and the hole are exposed to the outer environment directly, for example, water, and also in the here, polymer. So polymer corona page was just above the electrons and hole exciton pairs. And these polymers is also electron. They can have some kind of positive charge or negative charge. Or also anyway, it is electrons. So when the plus charge is more close to the electrons, they are having some kind of attractive field. And when the minus charge is more close to the electrons, they have the repulsive field. So the movement of this what's so-called dielectric state is changing the fluorescence light. So for example, when the analyte went for the dopamines, dopamine comes to this binding focus, this excitons filling dielectric environment was changed by the binding event of the dopamines. Maybe the polymer structure itself is somewhat changing, or just dopamine is surrounding these electrons or exciton pairs. So with this kind of the phenomena, we can say that corona page molecular recognitions can induce the fluorescence change. But exactly how is we don't know. We do not have the measurement techniques to exactly finding out the structural change of the polymers or some exciton kinetics of the carbon atoms after binding to valence. So that is kind of unusual with challenging point. It will be different, maybe it will be different for each coronas, dopamine coronas, serotonin coronas, what other coronas, maybe different for each different techniques, hard to investigate, so could not be answered so easily. Okay, so that is the last part.
What between the AB?
AB is just A is including the water and B is just excluding the water, just to see more clearly. So it is just showing the surfactant above the carbonatives, and it is also including all the waters outside. But there is also water is now included, just it is hide in the molecular molecular dynamics simulation. Okay, any questions?
Go to the A. You can explain more about the single color applied for the 10-30%.
For example, they are just incubating, as I remember, the Comocat or Hipco SWCNT inside of the cell. So that is, it is a cell and this is the cell. And they are showing the fluorescence in just cameras. Then it looks like these kind of gray colors. But using the hyperspectral cameras, they can detect only like these lesions and only these lesions. They can measure each pixel's spectrum. Then each pixels does not have always the same carbonatives. Some, for example, 6,5 was here and 10,5 is here. So they can differentiate that kind of different carbonatives by the spectrum. And how to say it, showing that each different pseudo colors in the images. Then what we can do is that, for example, so we are using only one single chiralitis, for example, that is labeling the cancer cells, and other chiralities using for the normal cells. Then it looks like, to us, it looks like just the cells, but some carbonatives which have the cancer cell labeling techniques are showing like the lead. And the normal cell carbonatives can be seen as the blue. So using different chiralities to make them different roles and functions, and we can use not only one single wavelength, we can use multiple wavelengths, so multiple functions in the one images. So that is the good portion of the multiplexed imaging. And this is more higher degree, so it is a hyperspectral imaging, so not just 2 or 3, it can be 10 or 11, but how to first chiral sorting each carbonatives at the milligram scales to use that is kind of difficult. Very difficult. Yeah, because usually this lesion is more bright. So I guess the more there is not evenly distributed, some chiralities are more bright or more many inside of the mixtures. So I think the green is looks better and bright, maybe not by the numbers. I guess that is more still like brightness if it is corresponding to this spectrum. And maybe green is after when the red and blue was coincide, they are making the greens, and maybe that's one of the reasons. I'm not sure. Higher sorting, do you want to do that again? Higher sorting? 다른 교수님 지금 셋업 아직 뭐 문제가 생겨가지고 못 하고 있는데 그거 되면 하려고 하고 있어가지고 그때 했던 거 독일이랑 했던 거 녹화되고 있네. 그럴 수 있지. Any other question?
complicated.